Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. In today's lecture, we will continue the discussion on fabrication of cellular ceramics. In the last lecture, we learned about the basics of ceramic fabrication, where we discussed about the sintering process, the stages of sintering and sintering mechanisms. This discussion was required because, as I mentioned in the last lecture, that despite sintering being a bulk fabrication technique or bulk ceramic fabrication technique, several processing routes for porous ceramic fabrication also involves sintering. So, we learned the basics of sintering in the last lecture, and then we learned about two different processes for porous ceramic fabrication. One was partial sintering and the second one was freeze casting. In today's lecture, we will learn about three more common processes typically employed for fabricating porous ceramics. These include gel casting technology, sacrificial pore forming agents or PFA, and use of replica templates. The main keywords for this lecture are gel casting, sacrificial pore forming agents or PFA, pore formers, replica method, anisotropic porous morphology and biomorphic ceramic. So, we start today's lecture with a brief description of the gel casting process. Gel casting process is a very common method for fabricating porous ceramics with 3D interpenetrating structure. Gel casting is actually a wet processing technology and it is a rather simple and cost effective process. A simple flowchart for the gel casting process commonly employed is shown in this slide, along with typical schematic diagram of how the pore morphology forms in the gel casting process is also shown here. The process starts with the formation of a slurry. The slurry typically contains some organic monomers and cross linkers along with the ceramic powder. After mixing with the initiator and catalyst, some in situ polymerization reaction takes place and through this reaction the foam structure is formed. After the foam structure is stabilized, the drying of the gelled part is done in a controlled atmosphere and then the polymer burnout and sintering takes place as the final process to give the ceramic foam. So, gel casting process has many advantages. One of them is that, as I already mentioned, the process is very simple and also the process is extremely economic, but it also has certain limitations. One of the biggest limitations is that because in gel casting process some chemicals are used. So, these toxic chemical reagents can be a threat to the workers' health and to the environment. Further, there are some cases where the shrinkage of the gel casting process can also give rise to porosities. But despite these limitations, gel casting has become a very popular process for fabricating porous ceramics because of its high reproducibility, high yield and also good control over the pore morphology and its economic process. A typical morphology of a gel cast alumina ceramic is shown in this particular slide, where the left hand side is showing these gelled foams, where you can see that these large pores are visible and also the pores are interpenetrating. That means, there is a continuous channel between the pores through which multiple pores actually combine. That means, these gel cast components or the gel cast porous ceramics are also very good for filtration application, where typically infiltration of the gel cast part is done using some fluid like liquid. A higher magnification photograph of the gel cast sample of the inset part is shown on the right hand side, and there we can see that despite this process of fabricating porous ceramics, because the material was sintered, we obtain a good bonding between the individual particles, and that will impart the gel cast sample with sufficient strength for further handling. The next method that I would like to introduce at this stage is the use of sacrificial pore forming agents for fabricating porous ceramics. This is also one very simple technique for fabricating porous ceramics, and again the typical flow chart employed for fabricating such ceramics using this process is shown in this slide, and also the schematic morphology showing the microstructure development or porosity formation in this material during using this pore forming method is shown on the right hand side. This process has several steps. The first stage begins with the mixing of the ceramic powder and the pore forming agents. So, the pore forming agents, it can be anything, they can be like polymer wax, they can be like inorganic components like sodium chloride, it can be also like potassium carbonate, and also some metals having low melting point like aluminum, iridium. These can also be used as pore forming agents. So, the first step and one of the most important steps in this process is the mixing of the ceramic powders and the pore forming agents in a homogeneous manner. The word homogeneous mixing is very important, because if the pore forming agents are not mixed in a homogeneous manner, then they may actually agglomerate, and that will give rise to poor properties. Why? Because the microstructure or the porosity distribution will not be similar everywhere, and there will be regions with large pores and interspersed between small porous regions. So, after the proper mixing of the ceramic powder and the pore forming agents, the first task is the green body fabrication. We already learnt about the green body fabrication in one of the previous lectures. So, for this green body fabrication, we typically employ either cold isostatic pressing or uniaxial die pressing. Many a times these two processes are also combined together when the part is first subjected to uniaxial die pressing and then cold isostatic pressing. So, after this pressing stage, a green body is obtained, but as we already know that the green bodies, they lack sufficient strength for further application. Also in this particular case, because the aim is to obtain a porous body, this green body does not have sufficient porosity, because the pore forming agents, they are not they are still within the microstructure. So, after the green body is fabricated, the next step is the burning and sintering. Many a times burning and sintering steps are combined together in one single stage of sintering. There are also cases where first the sample is burned and then again further sintered. So, during burning and sintering, the main thing that occurs is the pyrolysis of the pore former, because the pore formers are many a times they are polymeric materials like polymer beads or polymer wax and so. So, when these polymer materials burn or decompose, they actually give rise to the porosity, and after the burning stage is over and after the sample is sintered, the material actually the porous foam is obtained, which has the porosity as decided by the initial pore former amount and content and their structure. So, few important points to remember here is that this process has become extremely attractive for fabricating porous ceramics, because this actually provides a very good and well mean to actually control the porosity and pore morphology. Because the pores are actually designed to actually assume the dimensions and shapes of the initial pore forming material or pore forming agents, and that is why the the dimensions and the shape of the pore formers, they actually control the shape of the pores, and this way we can obtain a very well defined porosity in such materials. And also the word sacrificial should be clear by now. The word sacrificial is used because in this fabrication technique, whatever pore forming agent is used, that is sacrificed, because after the fabrication is over, the pore forming agent is no more there and it actually forms a porous body with uniform distribution of porosity if it is fabricated in a proper manner. So, among the pore formers, as I already mentioned, there can be many materials used as pore formers. Typically these materials are low melting point materials. There can also be materials like carbon fibers, cellulose fibers, starch, polypropylene, polymethyl methacrylate, and also other metals like tin, indium, bismuth, etc. Also there are situations or cases where inorganic materials like sodium chloride is also used. If sodium chloride is used as a pore forming agent, then there is one final step after the fabrication of the sintered body, and that is called leaching out. In this case, the sodium chloride actually remains within the structure, and then if the sintered body is put under water for a sufficient amount of time, then the water will actually leach out sodium chloride, and one obtains a porous body from leached out sodium chloride samples. Some of the properties of the pore forming agents are extremely important to actually give a good pore morphology and pore structure. These include that the pore forming agents should have a sufficiently low melting point, because either melting point or decomposition temperature. Then it should also have similar expansion coefficient as the ceramic matrix, because if the ceramics matrix and the pore forming agent have vastly different expansion coefficient, that might actually give rise to cracks of the inside the body because of thermal expansion differentiation. This method is very attractive, as I already mentioned, and it can also provide materials with a very wide range of porosity, namely from 20 volume percent to 90 volume percent, and also a wide range of pore size from even 1 micron. So, very fine pores to even 700 microns or even higher. And as I already mentioned, this pore size is directly dependent or controlled by the size and dimensions of the pore forming agents. But one of the biggest challenges, or rather two challenges, are involved in this process. One I already mentioned, that is the uniform distribution of the pore forming agent. If the pore forming agent is not distributed in a proper uniform manner, then again we have non-homogeneous pore structure, which might actually lead to poor properties in the final porous ceramic. And the second problem is that, as with gel casting process, while using polymer pore forming agents, the burning and pyrolysis of the polymer can actually give rise to harmful gases, which are actually harmful for the environment and also for the operator. So, this slide actually shows the many different ceramics which have been actually fabricated in literature using such pore forming agent process, and as we can see, there is very less restriction over the ceramic type, and many materials like alumina, silicon nitride, silicon carbide, yttria stabilized zirconia, and all these materials have actually been fabricated using this sacrificial pore forming agent method. Also, many pore forming agents have been used, as is being shown over here, like naphthalene, phosphoric acid, carbon black, rice husk, corn starch, sodium chloride, and so on. So, as you can see, many a times the pore forming agents that we actually use, they are actually very economic, very easily available and economic materials. So, the overall cost of the process is also pretty economic. And also, as we can see, the porosity actually also varies over a wide range, as is being shown, like starting from around 20% porosity to even more than 70-75% porosity. So, this is a very versatile process which can actually give rise to a wide range of porosity and pore morphology as per the design requirement of the initial material. Some typical microstructures of this porous ceramics using the pore forming agents are being shown over here. The left hand side image shows a microcomputer tomographic image of an alumina foam using some polymer wax as pore former, while the right hand side images show the SEM images of a silicon carbide foam also using some polymer wax, and in this case the size of the polymer waxes was varied, and as you can see, we had two different types of polymer waxes were used. One had a spherical shape with coarse morphology, and the other one was a fine shape with kind of uniform morphology, and as you can see, these give rise to very well defined and varied morphologies. The next technique that I am going to introduce at this point is the fabrication of porous ceramics using replica templates. Now, again this is a very common technique for fabricating porous ceramics, but this technique is commonly used for fabricating ceramics with a very large amount of porosity, even more than 90% porosity. So, this process, it has also some other names like the lost mold process or Schwarzwälder method. So, this process actually begins with a replica. So, this word replica foam or replica method comes from the fact that we need initially a replica. This replica can even be a packing material like a packing foam, which can actually be used to fabricate these porous ceramic bodies. So, the first, once this replica has been chosen, because the final dimensions of the pores and the pore morphology and the pore size, they actually depend upon the morphology of the initial foam replica that is being chosen and its dimensions and morphologies. That means, the initial selection of the polymer foam is very important. So, after this polymer foam is selected, the first step is the fabrication of a ceramic slurry. The ceramic slurry should have sufficient rheological properties and also good, sufficient and well defined viscosity. So, the first step is that this replica foam is actually immersed into the ceramic foam slurry, or other way around, the ceramic slurry is impregnated into the open porous or this replica foam. And the idea is that all the struts, as you can see, this polymer foam has thin struts, and all the struts of the polymer foam are actually uniformly covered with the impregnated ceramic slurry. After this impregnation step is over, the next step is the removal of excess slurry and drying. This removal is typically taken place under a rolling action. That means, this impregnated foam is actually passed through rollers, and through this action the excess slurry, the excess ceramic slurry is ejected, and we obtain a very uniform distribution or uniform coating of the ceramic slurry on the thin polymer struts. After this coated body is obtained, the next stage is as always burning and sintering. During the burning process, the polymer core, that means this polymer struts cores, they actually decompose, and that actually gives rise to a continuous this and only the ceramics, this ceramic coating on the struts, that actually remain. So, after this thing is obtained, after the ceramic foam is obtained, then this ceramic foam actually takes the dimensions of the initial polymer strut. So, this way, as I already mentioned, the selection of a proper dimension and shape of the initial polymer foam is extremely important, because that actually controls the final dimensions of the ceramic foam and its porosity and pore morphology. Now, few things are again very important over here, that so the first thing is that these ceramic slurries, this process has lot of advantages. The first thing is that it is again very flexible process, and it can also give rise to a wide range of porosity. However, at the same time, this porosity is mostly confined to the higher porosity level, like more than 80-90%, because at low porosity levels it might actually happen that the polymer struts, if the porosity is too low, then there is not sufficient space for the impregnation of the ceramic slurry, and the impregnation will not be that much successful. Another advantage is that this method can be used for a wide range of ceramics, because the only limitation is that the ceramic should be well dispersed in a slurry. That means, if the ceramic powder can be dispersed in a slurry in a uniform manner, then any ceramic slurry can actually be used for fabricating these porous ceramics using the replica technique. One drawback of this technique is that because these polymer struts and also the resulting ceramic coating on the polymer struts are very thin. So, sometimes during the heat treatment process they might actually burn, and that might actually give rise to some cracks or some defects inside the structure, which can actually reduce the mechanical properties. Otherwise, this structure has excellent permeability because the pores are very open and continuous, and again this is a very common material or fabrication technique for fabricating filters for many applications, high temperature applications, as we already mentioned in the application of porous ceramics chapter. Typical structure of such porous ceramics obtained by using this replica technique is shown over here. Here, as you can see, the right hand side image, the left hand side image actually shows the ceramic foam fabricated using the polymer replica, and here we can see a very nice uniform distribution of the porosities, which is controlled by the initial polymer slurry, polymer foam. And the right hand side image actually shows the SEM image of one such strut. There is one very interesting feature of this SEM image. If we see very clearly or look very clearly, we can see that at the middle of the strut there is one triangular hollow region, and this triangular hollow region actually originates because this was actually the original polymer strut which was actually used as the sacrificial template. And because this ceramic coating or the ceramic slurry actually coated over the polymer struts. So, that means when during sintering and burning these polymer struts actually pyrolyze or decompose, that actually gives rise to the triangular pores at the inside of these ceramic slurries or the ceramic struts. So, basically these ceramic foams fabricated using the replica template has porosities of different length scales. We have large pores surrounded by these individual ceramic struts, and these large pores actually determined by the dimensions of the initial pores in the polymer foam, and then we have those triangular struts in between the ceramic strut, and these triangular foams or continuous triangular foams, they actually form because the polymer foam which was used for the initial coating and pyrolyzing action, these actually got burned, and from that actually this triangular foam, this triangular channel kind of foam structure actually formed. Another variant of this replica technique is the fabrication of microcellular ceramics from wood. So, wood, as I already mentioned in one of the previous lectures on material selection, wood is an excellent natural composite material with excellent properties like very high specific stiffness, and also it has excellent damage tolerance and very nice microstructure. Wood actually possesses an open porous network of cells, and this open porous network actually provides us with the opportunity that the wood can actually be infiltrated easily, and that will actually provide us with a very nice initial preform kind of structure which can be actually converted into a porous ceramic body. Also, wood has another advantage, and that is wood possesses an open porous interconnecting network, and this open porous is again very important because that actually allows the proper infiltration. Typical microstructures of different kinds of wood are shown over here, and as we can see, these are very interesting microstructures, extremely varying, and these are unique microstructures. That means, this uniqueness cannot be actually fabricated by any of the artificial foaming techniques, because these are natural microstructures. And also there are two more features for this microstructure which are very important for porous ceramic fabrication. The first one is that, as you can see in many of the microstructures are non-isotropic or anisotropic. That means, there are microstructures which are different along different directions. If we assume that the vertical direction of this slide is one direction and the horizontal direction is another direction, we can see in most of the micrographs shown in this image that the pore morphology is kind of non-isotropic. Apart from this rattan wood and oak, where the pores are more or less spherical, otherwise we have a mixture of both cylindrical and ellipsoidal kind of pores, and that will render the structure a high degree of anisotropy. Another important aspect is that the pore structure of wood is mostly also a graded morphology. That means, as I mentioned in the previous lectures, thus many of the natural materials actually possess a graded morphology. That means, the microstructure varies as we change direction, as we move from one point to another point along at least one direction. And as you can see in these microstructures, the gradation of the microstructure is also very much observable in these images. So, that means that if this graded structure of the wood is kind of fabricated and kind of converted into a porous ceramic, then it should be possible to also maintain this unique microstructure of the wood, and that will actually allow us designing materials not possible with any of the conventional artificial porous ceramic fabrication techniques we have discussed so far. Now, the fabrication of wood ceramics or fabrication of porous ceramics from wood has several steps. So, the first step is basically the preparation of the porous biocarbon template. That means, the wood is basically the first step is called the pyrolysis step, which is typically carried out at around 800 degrees Celsius or higher. So, during this pyrolysis stage a graphitic carbon template is formed, and in the next stage the conversion of this graphitic carbon is actually made into or converted into a carbide ceramic or oxide ceramic. A detailed flow chart of fabricating silicon carbide kind of ceramics from wood in a cost effective manner is shown in this slide. So, as you can see, the process starts with wood, that means the morphology of the wood that you want, that means whatever porosity or pore morphology one wants. So, that kind of wood is initially selected, and after the first drying stage, the next stage is the pyrolysis, which is taken place as I already mentioned at temperatures more than 800 degrees Celsius. This pyrolysis typically takes place in a nitrogen atmosphere, and after that one obtains a porous biocarbon template. Once this porous biocarbon template is obtained, it is infiltrated with liquid silicon, and then this silicon will actually or part of the silicon will react with carbon at those temperatures to form silicon carbide, and the rest actually remains as silicon, pure silicon. So, this way actually we can also obtain a porous ceramic composite, where it is a composite of silicon carbide or C6 ceramic. One can also infiltrate with gases like silicon oxide or CH3 SiCl3, and in this case one obtains only a porous SiC ceramic, and these porous bodies also can have excellent mechanical properties depending upon the pore morphology and the initial structure. So, we conclude at this point. In today's lecture, we discussed about 3 different techniques for fabricating porous ceramics. We started with the gel casting technique, which we learned is a wet processing technique, which provides a very uniform distribution of interpenetrating 3D porous structure, but the main limitation of this technique is that it is often involved with toxic chemical agents which pose health and environmental risks. The second technique we learned is pyrolysis of sacrificial pore forming agents, which we learned is the powder metallurgy method, where the sacrificial pore forming agents and the ceramic powders are initially mixed together, and after burning and sintering we obtain a porous body, where the porosity and pore morphology depend directly upon the initial structures of the pore forming agents used. Again, this technique may also involve the evolution of some harmful gases, but this technique has the advantage that both the porosity and pore morphology can be controlled very precisely. The third technique we learned, actually 2 techniques we learned. One was the replica template, where initially we learned about those polymer foams or polymer sponges, which are actually used for fabricating open porous ceramics with a large range of porosity. And next we learned about the biomimetic ceramics, where wood was actually shown to be a very nice preform material, and after its pyrolysis and subsequent infiltration, the wood can actually be can be transformed into a very nice porous ceramic, again with a very unique microstructure, and it is also possible to fabricate graded morphology and also anisotropic morphology. The following references were used for this lecture. and in the next slide or in the next lecture we will learn about the processing of metal forms, and two different techniques will be learned in the next lecture for metal form fabrication. One is foaming by gas injection and the second process will be foaming by decomposition of blowing agents. With this I come to the end of today's lecture on fabrication of porous ceramics. Thank you very much.